Hi, ladies and gentlemen, it's Mrs. Jackson. I just wanted to go through acid-base dissociations one more time. I've had a couple of students ask questions, so we're going to do a quick review of acid-base dissociations for weak acids and weak bases, and for strong acids and strong bases, looking at how they're similar and how they're different. And then we're going to do a quick review as we go through with conjugate acids and conjugate bases. So let's go ahead and get started. First off, when you have a strong acid, remember we've talked about how essential it is for you to memorize that list of strong acids. Strong acids will dissociate 100%. And when I say dissociate, all I mean is when that acid is placed in water, the polar nature of the water molecules help to separate the hydrogen cation from the anion of the acid. So, for example, hydrochloric acid is HCl, one of the strong acids that you need to memorize. Because this dissociates 100%, we show the arrow pointing forward only. There is no reverse process for a strong acid or strong base to reform the acid. They dissociate 100% and stay dissociated. Okay, when they come apart in water, then what I get are hydrogen ions dissolved in water and the anion, whatever it is, chloride in this case, dissolved in water. Okay, so I have the dissociation of hydrochloric acid, a strong acid, fully 100%. So I use the forward arrow. Okay. The other way that you may sometimes see this is with the water included. I tend not to. I tend to use just the dissociation of the acid, but you can show it as it interacts with the water molecules. If you when showing that, it looks like this. You've got the water molecule. Water in this case is not a reactant as much as it is just a receiver, if you will, of the hydrogen ion. In this case, you would then show the hydrogen ion having associated itself with the water molecule becoming hydronium, and you still have the release of the chloride ion. Okay. In this case, if you're looking at conjugate acids and conjugate bases, which we typically don't with strong because they go only forward, this is your acid, and in this case, water is acting as HCl is the acid, water is acting as the base, the hydrogen ion acceptor. When we look at weak acids, however, it's a little bit different. So here is a set of weak acids, and this comes from your data booklet, page 19, which you have an assignment related to this later today. When you look at these, notice, and we've talked about this before, notice that they all end with that COOH. We haven't covered organic chemistry yet, but that functional group at the end, COOH, is always going to indicate that we're working with an organic acid, also called carboxylic acids. It's important that you understand it is only this final hydrogen that will dissociate when it's in water. But because these are weak, they don't dissociate 100%. So we write those just a little bit differently. Let me show you what one of those looks like. Let me move this a little bit out of the way or make it smaller. All right, so I'm going to start with one of the more common acids that we use, and that's right here, ethanoic acid. Ethanoic acid we use a lot in IB chemistry. It's also called acetic acid. So if you hear me refer to acetic acid, it's just another name for ethanoic acid. So with a weak acid, we start off showing the formula for our weak acid, CH3COOH. And with these, we can also show it with or without the water. I'm going to show it without the water first, and then I'll show you what it looks like with the water molecule. If I've got acetic acid, it is weak, which means it only dissociates partially, only partially ionizes. And so these I show with the reversible arrows because they do reach an equilibrium between the dissociated form of the acid and the full form of the acid. When it dissociates, again, you get the hydrogen ion in solution. That's this hydrogen right here. And then you get the remaining anion, just like we did with strong acids. It's just a different anion. And the remaining anion is CH3COO-. And that's the remaining anion. These are aqueous in solution. And that's how you write the dissociation for a weak acid. When we write it with water, it looks more like this. Okay, I still have my acid, CH3COOH, and this is aqueous. We show the water molecule like this, but it is liquid, so it will not be included in our Ka expression. It reaches equilibrium with the H3O, just like with the strong acid, and the remaining anion, CH3COO-. And all of those are both aqueous as well. Okay, so when we start to look at conjugate acids and conjugate bases, this is our acid on this side because it is donating the hydrogen. Under Bronsted-Lowry, water is acting as a base because it is accepting the hydrogen. On the reverse side, this is the conjugate acid. It's the base plus the hydrogen, so this is my conjugate acid. And the acetate or ethanoate ion is the conjugate base. Now, it's important that you understand, the stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. We will dive into that more when we start setting up equilibrium expressions on Thursday. But for now, okay, I want you to practice on writing your dissociations and identifying your acid conjugate base and base conjugate acid pairs. So my acid is connected to my conjugate base, and then the base is connected to the conjugate acid. Those two are related in solution. For weak bases, it's very similar. For strong bases and weak bases, it's similar, but it is different in a couple of important ways. Obviously, with a base, we don't produce additional hydrogens in solution. We have an abundance of hydroxides in solution as compared to neutral water. Strong bases are your alkali hydroxides, your alkali metal hydroxides, and the alkaline earth metal hydroxides. Sodium hydroxide's kind of a favorite of most chemistry teachers as a strong base. Again, when it says strong, you should understand that that dissociates fully in solution. So that's a 100% dissociation. And I get sodium ions and hydroxide ions in solution. So this usually begins as a solid. And then when we put it in water, these are dissolved in water, and so they are aqueous. Water is not a reactant, so we don't necessarily need to list it. And sodium will ultimately, when we start doing some practice problems, be what we refer to as a spectator. You learned about those when you were in sophomore chemistry. That means it's present in solution, but it does nothing. As I stated on the last slide, the stronger the base, the weaker the conjugate acid. So if this is my base, the weaker my conjugate acid, that's the Na of sorts. Okay, so this does nothing in solution. We don't generally show these strong bases with water because we are not losing or donating a hydrogen. We've got the hydroxides. Normally, we just show them dissociating and we give them the aqueous tag because they are dissolved in water. With your strong acids and strong bases, when you calculate pH, it is the same as you're going to use the same concentration of hydrogens or hydroxides as the base did originally. So if you have a solution of sodium hydroxide, because it is a 100% dissociation, whatever concentration you have of sodium hydroxide is the concentration you will have of the hydroxide ions. Those are the types of calculations you've already learned to make. We will be learning how to do pH calculations with weak acids and weak bases on Thursday. With weak bases, these are similar in concept to the weak acids. They do not dissociate fully, or they don't fully give the concentration of ions when they initially dissociate as your strong bases would do. So I'm going to show you what these look like. We generally will work with the weak bases, the amines. This is on page 20 of your data booklet. Ammonia is one of the most common to use because it is one, easy to work with when you do instruction, but number two, it's just very common in industry and elsewhere. So when you are writing the dissociation, as it were, for a weak base, it's important that you recognize everything is going to happen at this NH2 or NH3 or NH. By nature of nitrogen, if you remember, has a lone pair of electrons. So nitrogen has one lone pair of electrons, and it generally forms 3 bonds. All right, and it's this lone pair of electrons that have a negative charge that are going to be attractive to hydrogen ions in solution. So let's look at what this looks like in practice if we're going to write the dissociation equation for any of the weak bases. I'm going to demonstrate with ammonia, and then you're going to practice with the remaining set. Let's see if I can shrink this just a hair. All right, so we're going to take ammonia and write its dissociation. I've got NH3, and when we show the reaction or the dissociation of these weak bases in water, we do need to show the water molecule itself. And I think here in a second, you're going to see why that's going to be so important. So when I have my dissociation of ammonia in water, what happens is, and if you were in my chemistry class as a sophomore, sometimes we look at water as an HOH. So I've got hydrogen ions and hydroxide ions, just like when we looked at the ionization constant for water. What happens is when water exists, it will automatically dissociate, or it reaches an equilibrium of dissociation where I have hydrogen ions present in solution and hydroxide ions present in solution. This hydrogen ion here with its positive charge is going to be attracted to that pair of electrons on ammonia. And what we wind up with is NH4, because that hydrogen ion is attracted to that pair of electrons, but it carries a positive charge because I have the hydrogen ion is a proton without the electron. That's why it's the positive charge. When that hydrogen associates with the NH3, when it makes friends with NH3 to become NH4, that leaves hydroxide ions in solution. And this is why you wind up with an alkaline solution when you put ammonia in water, because the hydrogen from water dissociation is attracted to that pair of electrons, and that leaves me with the hydroxide ions in solution. By Bronsted-Lowry, this is a hydrogen ion acceptor, so this is my base. In this case, water is the hydrogen ion donor, so it is the acid. That makes the NH4 the conjugate acid, because it is the base plus the hydrogen. And that makes the hydroxide the conjugate base because it is the acid minus the hydrogen. So as I stated before, the stronger the acid or base, the weaker the conjugate species. And in this case, because I have a weak base, that means my conjugate acid is going to be stronger. So I hope this helps to clarify some of the concerns some of you had with writing dissociations. Be sure that you go into Schoology and finish the practice problems that I've assigned, because the understanding of these dissociation equations is going to be essential in setting up our acid-base equilibrium. If you can't set up your dissociation equations, you won't be able to set up an ice chart. So go through, get the practice finished, and I will see you on Thursday.